Hey there, math fans. Dr. Andy Lovelace here. I'm going to talk to you about something I've done for quite a few years in my Calculus 3 course, where I stop and talk about sort of the world of derivatives, the different flavors you can encounter. This is based off of 20 years of teaching 20,000 plus students. There always were these questions that would come up where I realized students they remembered something from related rates or something from implicit differentiation or something from somewhere else, and they were getting things mixed up. So I had this idea of, why don't I just address this the moment we do partial derivatives and lay out the world of derivatives. And so I've never done this, but no one else has seen this except my students, so I thought it'd be fun to share this same idea here and get your feedback on the world of derivatives. Okay, so ultimately derivatives are very valuable to find the slope or the rate at which something's happening. And then we can use that to try to predict the future. That's why people like so much what they do in differential equations and things of that sort. As I've thought about it, I think it really boils down to the derivative notation is giving us instructions on how to treat our variables. And of course, there's different ways we write it. But a lot of the confusion boils down to, at least for a beginning student, sometimes we're treating certain things as constants, as if they're just numbers. Sometimes we're treating something as an input variable, and sometimes we're treating it as an output variable. And depending on how we're treating it, then we're taking the derivative. So I'm going to go through the exact examples I've done in my class for years. It's just something I kind of invented years ago to add to my lecture. And so I'm going to talk about each of these types. And I'll have visuals along the way. So this is directly from my notes. We'll see how this goes, and maybe I'll redo this in the future, but let me know if this is useful to you. So first, I always talk about what students are most used to, a function of one variable. Now, it's usually not written this way. When you first encounter these, the variable is always by itself. That's the way we sort of prefer it. We sometimes write it as y equals x, sometimes write it as x squared, and that's that function on the right. And I always tell students, when you leave a calculus course, whatever else you've forgotten, you need to know that the function represents the height. Now, some students forget that in and of itself, which does bother me, but it's the height. So if I move a point along that curve and I give it like x equals 1.3, you can plug it in and find the height. It's 1.3 squared. But the height often is not all that we need. We also need the slope for many questions, and that's what we call dy dx. The reason we use Leibniz gave the dy dx notation, and it's pretty useful because the way we think about it is as slope, and in this case, it's 2x. So the slope at 1.2 or 1.3 is easier to compute. Just multiply by 2. But basically, it's this representation of the rise over the run. Casually, if you go over one step from there, you're going to go up whatever the slope is. And we can then get this line because we know the slope and we know the point. And we can ask lots of questions like, when is the slope 0? Which I jokingly say, calculus helps you find the bumps. That's when you want to know what the slope is. That's that game we've played. Okay. So the fact that we can find a function for both, very valuable. So in this setting, we're thinking of this as a function that represents height. We're thinking of the derivative as a function that represents slope, and all is well with the world. In a sense, we have taken the derivative of this side and rewritten it as y prime, but at the time we were learning that, we didn't think of it that way. Okay, let's keep going. Just going to scroll through. I do all these ones. So one is a function of one variable. We take the derivative. That's what we're most used to. I then always have a few students that say, I thought in related rates we had to do this weird thing where every time we took the derivative of a variable, we put a prime next to it. And students come to me and said, I have been programmed that if I'm differentiating with respect to t, to just write the derivative of y, think of it as 1, and then write dy dt. And then I take the derivative of the other side and have students say, okay, I get it. You just always write dx dt, dy dt, z dt. And they often then get confused when we talk about other derivatives. So that's a common question I've encountered. Oops, sorry, I didn't mean to move that. I'm trying to move this over. So what can I say about that? Well, what's happening there is we have a particle moving along the path. So in the last problem, x was like our input and y was our output. Now in this problem, they're saying t is our input, which doesn't even make sense when you at first blush, because there is no t in the problem. And they're actually saying x is an output and also y is an output. What they're actually doing is they're thinking parametrically when they say this. So I'm going to erase this for a second. They're thinking of it as a parametric function, basically where x of t is something, and I'll give you an example, maybe t, and y of t is something, maybe t squared. And it just so happens that every point on this parametric motion is also on here. We would say this is something that relates the quantities. It relates x and y. And if you can find something that relates x and y, then you can also give something that relates the rates. Now let me show you this here in a second. So here is this parametric curve. Now what it actually is, if you just look at the curve, it's something moving along that road. That's all it is. Something driving along this road. Now sometimes we're interested in the path itself. And the path itself is this. It's the same parabola as the last question. But this question is not asking what the slope is on the curve. It's asking how these things are related. It's saying, how does y change as a function of time in a situation where both x and y are changing? So there are no constants here. Everything's a variable. And in our head, we're thinking of the original expression as y of t and as x of t. Now, we don't usually write that, but we think of it as a t hiding inside those functions, so that when we differentiate with respect to t, we're basically using the chain rule. We do the derivative of y, which is 1, times the derivative, so it's y prime, or dy dt, as I like to write. And then we do the chain rule in the next one. It's 2 x to the t to the 1 times the derivative of the inside, which is dx dt. Once we get good at that, we don't write the x of t anymore. We just write dy dt is 2x dx dt. And if you know how fast the x is moving, then you also know how fast the y is moving. So if that particle was moving to the right or the left at like 3 feet per second, then you could put a 3 in for dx dt. That was that story. So that's valuable for motion questions. Okay, but the point is, if you look at that, everything has been a variable so far. Nothing is being treated like a constant. That's different than partial derivatives, which we're going to do in a moment. Implicit differentiation. The moment we have lots of variables mixed together, some students think of this. Implicit differentiation is very valuable and useful. Implicit curves, it's hard to study them without implicit differentiation. If I ask a grapher to graph this, it is not a function at all. It doesn't pass the vertical line test. It has all these unusual things for a given value. But a really interesting thing is we actually can compute the slope, and we don't need to solve for y. You could, but that would be a huge mess, and I would rather not. In fact, implicit differentiation is mostly something that saves us. Here's what I mean. So when I read this, this is saying this is the input, and this is the output. It just so happens that I can't get the y by itself very nicely. So for the rest of this problem, when I see these instructions, I'm thinking of y as a function of x. So even as it sits there, I can think of it as a function of x. I'm doing that because that's what the instructions are telling me. Okay, and I'm sure I'm taking too long here, but I think if you want an understanding of this, this is key. So here we have x, we have a function of x. Now details of when we can say an implicit function exists or how many implicit functions are there, that's a much bigger question. There are several different functions. You can split this into multiple functions, but now we're going to differentiate with respect to x. And now you can explicitly see it. There's an x here, there's an x here, there's an x trapped inside a y, and we just differentiate. The first term is 2x. The second term is a mess. So you have to think product, quotient, or chain. And you actually do need a product rule here because there's an x here and there's an x inside here. Everything is being treated as a variable. And if there's two variables in a term, you do need the product rule. That's something that students get confused of with partial derivatives, and one of the reasons I talk about this. So now we're going to do the product rule. First times derivative of the second times y times derivative of the inside, dy dx. So all of that came from here, plus the derivative of the first, which is 1, times the second, equals 0. And then we can solve for dy dx if we so wish. Sometimes we can just leave it like that. But 2xy dy dx is negative 2x negative y squared. And then we can divide by 2xy. I think that's pretty spectacular that we can actually do that. And I did it. I had to work kind of hard to make this happen. But here's an object on here. And I'm going to move it around in a second. And there is its tangent line. I was able to give it because I was able to compute that formula. And there's actually, for every y value, there's a couple tangent lines. But it works. You might say, well, aren't there two different formulas? Well, no, because I'm actually plugging in x and y for the slope. So you could have a whole bunch of different tangent lines for a given y or a given x. And I can find them all. No problem. Very cool, I think. And you can use this in all situations. So I really think of everything as implicit. Even the original one, I think of differentiating both sides now. Okay, so it broadens our understanding of what a derivative does. Everything there so far has been a variable, either an input variable or an output variable. Okay, so when you get to partial derivatives, we say, well, now there's a bunch of variables in the problem, and we're only going to consider some of them. So this little symbol, this partial symbol, is saying I'm only going to consider the slope or the rate for those two variables, and I'm going to ignore the rest. So this is a very important distinction here, which is that x is our input, z is our output, and we're thinking of it as a function of x only, and everything else in the world is a constant. So when I go to take the derivative, I'm really just looking at these, and the y's are being treated like numbers. Now, what does that actually mean? And that's part of what we talk about. I'm going to give this example. Here's this function. It's actually a surface. And I didn't mean to graph everything just yet. Hold on here. So what we're doing when we say we're fixing y is we're actually intersecting it with a plane. Now, the moment we do that, zoom out a little bit so it looks better, it now becomes a 2D question, a 2D curve. And I can actually show it to you. And then I can remove. And that's what we're doing. So we're changing the problem into a 2D problem, and then we're finding the slope on there. And that's it. But we have to understand that when we do this, we're finding that slope. Okay, so when we do this, here's what that looks like. We say, okay, we're going to differentiate this, this, and this, and treat everything else like it's a constant. So the derivative on the left is just 1 dz dx. So I actually did differentiate this. The derivative on the right is 2x. The derivative of a constant is 0. So I'm treating that like a constant. And the 5 and the y to the fourth are actually coefficients. They're like numbers. The derivative of x is 1. So you get this slope that says, okay, you give me the x value, you give me the y value, I will look in the x direction, and I'll tell you the slope. And it's a very physical thing. There's nothing mysterious about it. It's that slope. And then we can ask questions like, when is that slope 0 at a given value? So I can go here, what's that slope? And we go, well, that's great, but that's only looking at like one point in one direction. So it'd be nice to get the other direction and see if there's a place where the slope is 0 in both directions. And that's really what we do. Partial derivatives make more sense in combination with each other to find like the low point at the bottom. Okay, so that's what we're doing here. So when you see this set of instructions, z is the output. So we're going to say z is a function of y. Y is the input. And now x is a constant. And the hardest part for students is just this shifting of gears and the fact that suddenly y is an input variable. It's mostly a challenge of focus. It's not really new rules. But you might notice common questions I get are, why didn't we use the product rule here? Well, because only one of those things was a variable. There was only one variable there. That's different than in this last problem, where both of them were being treated as variables. I hope that makes sense. It's all about what is being asked. Okay, so now we're going to say y is a variable. This is a variable. This is a variable. Let's take the derivative of both sides. That side is dz dy, because we're thinking of z as a function of y. This is 0. This is 3y squared. The 5 and the x are coefficients, and this is going to be 4y to the third. So altogether, you get dz dy is equal to 3y squared minus 20xy to the third. These are two very important and valuable measurement tools, but they're measuring two very different things. So now we're looking at what happens if we intersect with the x-axis. We find the curve. So we're finding these two things, those two slopes. Maybe I can get rid of this just for a second. You can see this. We're finding those two slopes. We're basically taking two snapshots of our surface. Our surface is this, but we're just looking there. We're hoping that we can find a place where both slopes are zero, because just like in one variable calculus, we'd like to find the bumps. And there is a bump right there, I think, a minimum. Or maybe it's a saddle point. Hard to tell here. Yeah, it's a saddle point. Okay, anyways, that's what that means. So the partial symbol means something is being treated like a constant. All right, last one. So this sort of puts everything together. Students don't like these questions, but this is partially why I talk about this. Now we get the following, which really makes us think carefully. What if I have a situation where it's hard to get z by itself, but we have the same rules? So this is going to be the input. Z is going to be the output. And y is a constant. So in the moment you do that, you go, okay, I have a variable here. I have a variable here. I have a variable here. And now we're going to differentiate all of them. So it's going to be 2x plus y squared minus 2z dz dx equals 0. We differentiated everything with respect to x, treating z as a function of x. If there had been a z in this term, then we would have needed to do the product rule because there would have been two variables, but in this case there was only one. And then you can just solve for dz dx, whatever that is. Dz dx is negative 2x minus y squared over negative 2z. And that surface I can give implicitly with the help of a graphing device. It's very cool looking. Similar to what we saw before, but a 3D version. And I can find the slope anywhere. I can go that way. I can find the slope in that direction. There's two slopes because this is implicit. It's pretty cool that we can find such a thing. All right, I think I'm going to stop there because I hear a kid calling me to come read to them as they're going to bed. But I hope that gives you a flavor of the different roles of our variables, the different derivatives. The partial symbol basically is saying some things are being treated as constants. The rest, once you understand the roles of your variables, then you understand why we have these different derivatives. All right, thanks for listening.